right. Well, let's start. So last time I told you a little bit about quantum mechanics. I remind you how we do canonical quantization. And also, well, for most of you, showed you how we define path integrals, the path integral formulation of quantum mechanics. And I said also that these two lines are also how we will describe quantum field theory. There is the canonical approach, the operator approach, formalism, and there's the path integral formalism. And I guess phenomenology-oriented people are more interested in the canonical or operator formalism, whereas more theory-oriented people are more interested in the path integral formalism. But in principle, either one is good enough to do any calculation. Some calculations are easier depending on the formalism. So that is why I believe that in order to have a good quantum field theory education, you have to be proficient in both. So I will, in these lectures, I will go through both formalisms. And today we will start with the canonical quantization, specifically for the simplest example of a scalar field. But before we do that, let's remember the things that we said very shortly, the things that we said last time. So we said about the operator formalism, or canonical quantization. So that the formalism is related to the Hamiltonian formalism in classical mechanics, where there's a Hamiltonian H depending on P and Q. And more generally, you can have various functions on this phase space P and Q. And for two such functions on the phase space, we have defined the Poisson bracket as sum of the degrees of freedom of the system, df dqi, dg dpi, minus the opposite, df dpi, dg dqi. And then we've seen that canonical quantization basically amounts to replacing the Poisson brackets for functions of space, for C-number functions, for commuting numbers, into 1 over IH bar times the commutator of operators, operators being things that do not commute. And in doing so, we have seen that in particular, the fundamental Poisson bracket, which just comes in substituting P and Q for F and G, which is minus delta ij, becomes the commutator PIQJ minus IH bar. And then, moreover, by considering the harmonic oscillator, we have seen that this commutation relation implies A dagger equal to 1, where A dagger start the life as some combinations of P and Q in the classical Hamiltonian, but then at the quantum level they become creation and annihilation operators for one excitation of the oscillator. Okay? And I told you that also that a harmonic oscillator is the most basic example, but also if you understand it well enough, you can do everything about quantum field theory. First of all, you can think of, as we'll see today, you can think of any field in a first approximation, a quadratic approximation of the potential. You can think of it as just a collection of harmonic oscillators. And then any interactions the field can be understood as just perturbations around this system. So in other words, if you understand the harmonic oscillator, you should be able to understand everything. And just for completeness, we'll not do it today, but let me just remind you also that we had the path integral formalism. So I started by thinking about the transition amplitude between a particle at position q at time t and a particle at position q prime at t prime. And we wrote this as a path integral, right? We wrote this as dq e to the I s of q. But then we generalized and we considered variables that we call correlation functions or endpoint functions. Just these things with insertions of time-ordered combinations of time-ordered products of q of t's. These came from these guys. And then finally, we used an idea of generating functional, a simple mathematical idea to put together some functions. And we've defined a z of j as a path integral dq e to the I sq plus I integral dt j of t q of t. Right? And then we've seen that by taking differentiations with respect to I j of t, and then putting j equal to 0, we get these endpoint functions. Okay? And as I said, these endpoint functions are not obvious things to calculate for the case of a quantum mechanical particle, but they become the relevant things in the case of quantum field theory. Correlation functions are things one is used to, if you talk about, let's say, condensed matter, you can calculate correlations between some variables like spin or energy or something like this. So a correlation function would be, let's say, a 2-point correlation or a 3-point correlation between these variables in a material, or in cosmology, an important quantity that we calculate is the correlation function on the sky between fluctuations, thermal fluctuations, but any kind of fluctuations would do in principle, right? So we calculate the variable, the correlation function like this, just that instead of q of t, the thing that makes sense is some function, temperature in the case of temperature fluctuations, and not of t, but of the position on the sky. Okay? And, but to make contact with this idea of propagation that we understood from here, the correlators can also be factorized in a certain way that we'll see, and related to scatterings of particles. So in quantum field theory, then these kinds of objects are related to scattering of particles. So from that, you can see that this is more closely related to the idea of propagation of particles in quantum mechanics. All right. So this was a quick recap just to understand a little bit better what we did. But now let's proceed with canonical quantization in the case of a scalar field. And first, let's consider the kinematics of this quantization. So, obviously, the way to consider the scalar fields is to try to do a sort of discretization such that we can apply directly this formalism. So this formalism works for a set of particles. So you can think of the field as some sort of generalization of this set of particles. You can immediately write down the quantization. So first we have these variables on phase space. So what do we consider them corresponding to in a field theory? Well, first of all, if we're talking about some scalar, it's some function of x and t with a certain transformation property, but this is the same as prime, right? But, so it's a function of x and t. And as I said before, we can think of discretizing somehow this x. So we will have something like phi I of t, where I stands for x in some sense. But dimensionally, that doesn't quite work out. So in fact, what we need to do, the reason you can see this perhaps in the following way. This has dimension -1, it's a length, whereas this has dimension +1. Well, we'll see that later on why that is. Maybe let's not say it right now. But for the dimensions to work properly, I need something here with dimension -2. And oh, sorry. Yeah, that doesn't quite work out. It should have been then square root delta t. Okay. All right. So forget about this. I thought this would work. Because if this would be just spatial, it needs to be just spatial volume. If it would be space-time volume, it would work out, but spatial volume doesn't. Ah, well. Okay, yeah. If I would also add square root delta t, the dimensions would work out well. I'm trying to think why that doesn't work. It's bizarre. Well, let me continue. At least we know that the proportionality should be with square root delta v. So correspondingly here we will also need the same square root delta v, simply because this is these relations have to do with the index I, and therefore the same formulas should be valid for all the members of the phase space. So for cube P together, with respect to pi together, where pi is the canonically conjugate to the same phi. All right. So we want to write something like this relation. We want to define this Poisson bracket. Okay. So how do we go from one to the other? Well, so now that we have defined, we have some phi I of t and pi I of t, and we can think of this as simply, except for the square roots, we can think of them as simply q's and p's. Then I can define these derivatives of functions of q's and p's with respect to q's and p's. But the question is, how do I define this in the continuum limit, right? That was our initial question. So we define that 1 over delta v d phi j, df d phi j, should be, and now it should be some sort of derivative with respect to the function phi. But if this is a function, then f itself is a function of a functional, right? A function of a function is called a functional, right? And then the derivative has to be replaced with a functional derivative. So this would be a functional of j and t, and pi xi t. Oh, let's say xi. Right? The point is, the t dependence is explicit, but that's common to everything, so that's not the issue. The issue is the dependence on x, right? And the function, but f itself cannot depend on x. We have an implicit summation over I, which stands now for x, right? So that means that indeed f is supposed to be a functional. So in case you're not familiar with the idea of a functional and a functional derivative, let's consider this simple case. Let's consider the functional of the function phi squared of the function phi, function defined as phi squared over 2, but then in order not to depend on x, we have to integrate over it, right? Then the functional derivative with respect to phi of x and t is what? Well, the result, since this depends on x, the result has to also depend on x. Which means that the logic is, when I take the functional derivative, I just delete the integral and act afterwards as if it's a normal derivative. If it's a normal derivative, phi squared over 2 differentiated with respect to phi gives phi, right? So this is phi of x and t. Okay?
So
yeah.
What is the reason that we have to this extra effect of 1 over delta v in the recipe to?
Well, let's see that. I was about to say that next. All right. So we want to mimic this, right? We want to mimic this equation. So how do we write that? Remember that now f and g are functionals, right? So I have a sum over I. That's an integral now, right? Integral d3x. And now I would write df d phi of x and t, dg d pi of x and t, minus df d pi of x and t, dg d phi of x and t. Right? And you see, so if I just substitute in here blindly, I say df d phi I square root delta v, dg d square root delta v, d phi I, right? But then the no, sorry. Yeah, how should I say? No, that's right, yeah. And now I also said that df d phi is delta v times the function differentiation. So this thing is 1 over delta v times df d phi, delta v df d phi times delta v dg d pi, right? And so we got the delta v, that is d3x, right? Over which we sum. Okay. So.
So it's for us to get an element of volume to get the integral instead of the sum. Is that it?
I'm sorry. Yeah. So sum over I is in general is supposed to be well 1 over delta v integral, right?
Right.
For dimensional reasons. This is adimensional, and this, yeah.
So that is actually square of delta. That is.
I'm sorry?
That is the square of delta t. Put square of delta t.
Yeah, I mean, there isn't. I just said, I put this in here just to say that dimensions would work out in the first, if you put it, but afterwards you have to remember that it's just just the proportionality with delta v is relevant. Okay. So now that we've defined this functional Poisson bracket, then we can of course immediately find the fundamental Poisson bracket, this one, right? So now we say phi of x and t with phi of x prime and t, Poisson bracket is delta of x minus x prime. And the other ones are 0. And pi x and t with phi of x prime and t, Poisson bracket is 0. And note that as before, so here I wrote these things, but implicitly these were functions of the same time t. Now they're also at the same time t, so equal time, right? But space is different because space corresponded to this index I. So now I have phi of x and t with phi of x prime and t. So first of all, let's see that this is correct. Right? So let's directly substitute. So if I put f is equal to phi x and t, and g is equal to pi of x prime and t, right? I have well, the second term is 0, and then the first term is so d phi of x and t with respect to d phi of x prime and t is delta of x minus x prime, right? Because I said functional differentiation corresponds to removing an integral, right? So the point is I can write this I can write this as an integral d3 x prime delta 3 of x minus x prime times phi of x prime t, right? Phi of x and t can be written formally as an integral with a delta function, right? And so when I take a functional differentiation, I remove the integral, and of course remove these as well, and then I'm left with just the delta function, right? Okay, so if I write phi f is phi and g is pi, then this is a delta function, this is another delta function, right? But then I have, well, let's write this more precisely, otherwise we'll get ourselves confused. Do this example here. So I said df d phi of x and t with respect to d phi of x prime here, x and t is delta 3 x minus x prime. So then when I have the term integral d3 x, let me call it y, d3y, then I have d phi of y and t d phi of x and t d pi of y and t d pi of x prime and t, right? That's the term I have. And I said this is d3 x minus y, this is d3 x prime minus y, and then I have integral d3y. So by cancelling that with this, I replace this with x prime, right?
Actually, dy's should have been should be delta phi of x with respect of delta phi of.
No, I have I mean, I want to calculate this thing, right? I have the Poisson bracket phi of x and t with pi of x prime and t, right? So
I mean,
this is
in the definition of the Poisson brackets, you do the summation over the indices of P and Q, right? P and Q.
oh, sorry, sorry, yeah. Okay, fine, yes.
But the result.
Yeah, this was yeah. Whatever. Yeah, it's the opposite, but the result is the same. So y x prime y. But the result is still the same, right? Yeah. Okay. So we notice that these are the fundamental Poisson brackets, which means then that when I quantize, I get, when I quantize, I said I just replace the Poisson bracket with 1 over IH bar commutator. So we'll write equal time commutation relations. Well, let's write first the pi one. This is, sorry, this is IH bar delta 3 x minus x prime. And then phi with phi is 0. And pi with pi is 0. Okay? But the only thing I have to remind myself is what kind of operators these are. So these are now all operators when I quantize. But we said last time, we said last time that really what I have are Heisenberg operators. So phi h, x and t, right? Because these are operators who have an explicit time dependence, right? So that means that we're in the Heisenberg picture where operators depend on time, but states do not. However, we'll see later on that we'll have a variation of this Heisenberg picture, which is called the interaction picture. But for the moment, let's consider just this. Okay.
Professor,
Yeah.
just out of curiosity, isn't that strange that we say that when operators depend on time, they are in the Heisenberg picture, but we can have Hamiltonian's dependence with time dependence on the Schrödinger's picture also, don't we?
Well, in principle, you can consider also Hamiltonians that depend on time. That's right. It's kind of more unusual. However, it's not the common case, right? Hamiltonian depending on time corresponds to, say, transitions between states, right? But so this is something that we'll consider later. That's what we're interested in quantum field theory are not free fields like the harmonic oscillator, but we're interested in interactions where stuff happens, right? And in this case, we will use what I just said, the interaction picture. And then there's a difference between the interaction and the Heisenberg picture that is very important, and we'll see how to deal with that. But at this level, for harmonic oscillators, we do need to think about that. We don't have time dependence. All right? Good. So, next. Next, we consider a Fourier transform, but only over space, since we saw that time is special. So let's consider the Fourier transform. similarly for pi's. Okay. And inversely corresponds to saying that phi of p and t is integral d3x e minus ipx phi of x and t, and pi p and t integral d3x e minus ipx phi of x and t. Now, the 2 pi cubed is because we have actually the Fourier transform corresponds to 3 Fourier transform over the 3 spatial coordinates. And for each one, you know that it has to be, because the Fourier transform of one is 2 pi delta, we have to have a normalization of 2 pi. And I've chosen to include it in this relation so that there isn't in this other relation. Okay, so why did we consider this Fourier transform? Well, because as we will see very shortly, the momentum modes will act as harmonic oscillators. So like for the harmonic oscillators, so like for harmonic oscillator, we define the A's and A daggers, but now they depend on K and T. And I'll keep using omega, but since it depends on K, I'll put an index K. Okay, so I haven't told you who omega is. We'll tell you shortly when we go to dynamics. For the moment, we're talking about kinematics. But the only thing that we need to know is that it depends on the modulus of K. In fact, we will see that it's equal to square root K squared plus n squared. But the point is, it's some omega that depends on K, and then I just copied the formulas from the harmonic oscillator, right? All right. So I now substitute this into the original phi's. So I solve for phi and pi from this relation in terms of A and A dagger, and I put back in this Fourier transform and obtain so integral d3p over 2 pi cubed e to the ipx, and then the phi itself, which is A depending on P and T, e to the ipx plus A dagger P and T, e minus ipx, and then 1 over square root 2 omega p. Okay? Okay, and similarly for pi, integral d3p 2 pi cubed into the ipx, and then the factor here is now minus I square root omega p over 2, and the same ap of t e to the ip sorry, yeah, e to the I px plus a dagger p of t, p minus I px. Yeah, I guess I should have said so. Yeah, the first. So another way of writing this is to note that I can just replace the integral of p with the integral over minus p in the second term. And then I have e to the I px as a common factor. And this depends only on the modulus, so it doesn't change. And then I have here a pt plus a dagger minus pt. And pi similarly. Okay. But I've written them in this way with a e to the I px and a dagger e to the minus I px, because we will see what happens when we consider the quantization of the dynamics. These different terms would correspond to, well, creation and annihilation, and then correspondingly we'll have positive and negative energies. So we will separate these two terms according to the energy. But for the moment, this is just a mathematical trick. Okay. And now, so this is really just following up what we did for the harmonic oscillator with some integrals over p. So with a Fourier transform, but otherwise I just followed the harmonic oscillator. And so it's not a surprise, you can check for yourself that knowing the fundamental commutation relations for phi and pi, we can find the same relations for a and a dagger as we did for the harmonic oscillator. Namely, a commuted with a dagger is 1, or in our case, delta. So we obtain a IFT with a dagger p prime t is delta 2 pi delta p minus p prime. Well, let's check one of them. So, and the other one is 0, right? So a pt with a of p prime t is 0, and a dagger pt with a dagger p prime t is 0. So let's check the most relevant one, the phi with pi. Convince ourselves of that. So, you know, I could do the reverse case. I could just solve for a and a dagger in terms of phi's and pi's, and then directly commute a with a dagger, which are some long functions, and use these commutation relations to obtain this. But I will do the reverse because it's quicker. So I'll calculate phi with pi, assuming this, and we'll see that we obtain I delta. So this is what? There are two integrals over p and p prime. Then I have let's see, so I want to use this formula because I want to use A of t and A dagger of A of t and A dagger of p prime. So I will use these factors, and here these factors. But first let me write the common one. It's 1 over square root 2 omega p times 1 square root omega p times minus I square root omega p prime over 2. Right? These are from the two integrations. The integration over p came with 1 over square root, and over p prime with minus I square root over 2. And then what? Then I commute these four factors, right? But if I commute A e to the IP with A e to the IP, I get 0. A with A is 0. Also, if I commute A dagger e to minus IP with A dagger e to minus IP, I also get 0. So the only non-zero case is A with A dagger and A dagger with A, right? So I get a term that is A with A dagger, that's delta, times e to the IP, e to the minus IP, right? So this is IP minus P prime x delta delta P minus P prime. Okay, that's one term. And then the other term is from this one, A dagger P with A. So that's
Professor,
yep.
why does the x have the same? Aren't there two different x there?
Oh, sorry. Yes, thank you. Yeah. Thank you. And then
P prime 2, right?
P prime, right? Px, P prime, x prime. Thank you. And then and then the other term is A dagger. So I could use both forms, but I decided to use this form in particular. So now I have e to the minus I px plus I p prime x prime, and then also delta 3 p minus p prime, and this came with a minus, right? Because I had A dagger with A. Okay. Yeah, and I had forgotten to say, and nobody corrected me. So in this second form, when I changed p with minus p, I had a minus in the second form. So if I use the second form, I would see that there are already two minuses. So I can use it now. I can use now the second form, right? In this second integral, I change the integral of p prime with minus p prime, right? Yeah. I changed p prime with minus p prime. And then I need another color. And then I get plus in here. No, something is so I got the -1 from the fact that I had a dagger with A. Okay. And yeah, okay. No. Just yeah. How do I make this equal? I'm getting myself confused. I need to give a common factor, this e to the I'm doing something wrong here. Not sure what.
In one term, you can substitute p prime and in the other just p, right?
Just
so
p, okay, so I get plus here.
Isn't it?
Okay, so now I have the same thing. But if I do this, yeah, and then I also have p plus p prime, and here minus p, but delta of minus something is equal to delta of something. Okay. But I don't get the relative minus sign, so why? What did I do wrong here? I'm slightly confused. What did I do wrong? I'm getting really confused. So I have A with A and a dagger, and then oh no, sorry. Yeah. Sorry. That is of course the point. Yeah, this was a minus. Right? Yeah. And the minus was just here. Yeah, so there was a minus in here. That was the point, of course. There was a minus in pi. And then together with the other minus, I get a plus in here. Okay. And then, as we saw, we get the same e to the I px and the same delta. So these two terms give just twice delta 3 p minus p prime e to the I px plus I p prime x prime. Right? And then when I do one of the integrals, let's say p prime, I cancel this, and then p comes with delta x plus x prime. No, again, I got a sign wrong. There was p minus p prime supposed to be y.
The delta of p plus
Oh, p plus p prime, thank you. Yes. Good. So now I get delta minus x prime, x e to the I p x minus x prime. And yeah, when I do the integral over p, of e to the I px, I get delta. Right? So the final result is indeed delta 3 x minus x prime. Okay? And then these things cancel, and the square root 2 cancels with a 2. Okay? All right. So we do get indeed just 1. Okay. An observation is that I have not used at all the form of omega. I said that omega would be shown to be this, but I haven't used it until now, right? I only used the fact that omega was only a function of the modulus. I didn't use the explicit form. But now let's consider the explicit form. So let's say now dynamics and time evolution. So we'll consider just a free scalar field, which means no potential, right? Well, no potential, I said when I will consider separately the mass term. So we'll have a mass. And if you remember what we said in the first lecture, where we reviewed a little bit the scalar field, that means the Lagrangian is this kinetic term, minus a half d mu phi, minus a half m squared phi squared. As I said before, this is, strictly speaking, also a term in the potential, but in here I chose to consider it separately, and I mean, perhaps, let's say, no interaction, so no terms higher than quadratic. Okay? And the action is the integral of this. And so inside the action, I can partially integrate one derivative and write plus a half phi d mu phi minus m squared phi squared over 2. And the equation of motion is the Klein-Gordon Kg equation comes when varying this with respect to phi. I mean, so there's two ways, right? I can say the Euler-Lagrange equation where I differentiate with respect to d phi, but a simpler way to think is I just differentiate, I do differentiation with respect to phi, but after I do all corresponding partial integrations. So if I do this here, I can see, I can put both integrals either on, to act either on this or on this, and two partial integration will give a plus. So it's the same thing. So when either I differentiate with respect to this or this, I get the same thing, a factor of 2 that cancels the half. Therefore, the equation of motion is just 1 times d mu d mu acting on phi. And then differentiation here, phi squared over 2 gives phi. So this is minus m squared phi is 0. Okay? So the Klein-Gordon equation is d mu phi minus m squared phi is equal to 0. Or explicitly separating time and space, minus dt squared plus dx squared plus m squared phi is 0. Okay? And as we saw, it's useful to do a function, to do a Fourier transform over space. Indeed, if we do that for the p modes, the time derivative remains the same, and I multiply everything sorry, what did I write here? And this is sorry. Yeah, so I multiply everything with minus sign, and then I get, or maybe not, maybe just leave it minus sign in here. So minus dt squared then derivative x acting on e to the ipx gives ip. So derivative squared gives ip squared, but that's minus p squared. Sorry, there was a minus here. And so the resulting equation of motion, as we see, is the same one as for an harmonic oscillator with an omega squared that's p squared plus m squared. Okay? So the equation of motion of the free scalar field is just, for each momentum mode, a harmonic oscillator with this omega p. So therefore, for each of these modes, we have an HP that is 1/2 p squared plus omega p squared phi squared. Okay, so then indeed we can follow, as we did before, the transformations of the harmonic oscillator and well, yeah, and these are this is what we did before. Okay? Yeah, perhaps let's use it, let's write this way. think this is better. So I have pi is canonically conjugate to phi, but then the omega depends on the p, which is the spatial momentum of the field. Okay? Okay, so this justifies a posteriori what we did before. So we've seen that for a free scalar field, it looks like a set of harmonic oscillators for which we do the usual transformations. All right. Now, let's calculate the Hamiltonian for this system. Right? So, using the quantum mechanics idea, this would be what we would write. I mean, P was denoted by P in the quantum mechanics context. Now it's some pi. So this becomes now an integral of this pi of x and t, pi dot of x and t, minus the Lagrangian is also itself an integral of the Lagrangian density. So this itself now is an integral of a Hamiltonian density, which is just this, as we said in the first lecture. But now for this Lagrangian, which is minus a half phi dot squared, plus a half, this one, plus a half phi dot squared minus grad phi squared over 2. The momentum conjugate to phi is differentiation with respect to phi dot, which gives phi dot, right? Differentiation of 1/2 phi dot squared with respect to phi dot gives phi dot. So the canonically conjugate momentum to phi is also phi dot. And then substituting in here, h is phi dot squared minus a half phi dot squared, so that's phi dot squared over 2. And writing it in terms of pi, it's pi squared over 2. Plus a half grad phi squared plus a half n squared phi squared, right? So the Hamiltonian or energy density of the field is momentum squared over 2 plus grad phi squared over 2 plus n squared phi squared over 2. But we're interested to write, we're interested in writing h as a function of these a's and a daggers, right? So let's write the total Hamiltonian as an integral. And now I will write each term in here, all of the three terms are quadratic in phi. In phi's and pi's, and I will write each of them in the expansion, which I had before on the board, in terms of a and a dagger, right? So it's basically this expansion, but with an integral over p for each. So then, since each of these terms has two integrals, two fields becomes two integrals. d3p, d3p prime, and the exponentials, ypx plus ip prime x. oh, so yeah, let's write it I p plus p prime x. Then what? So pi comes with minus I square root omega over 2. When I square that, I get minus square root omega p prime over 4. But then I have also 1/2 in here. So 1/2 with square root of 4 gives 4 in all. And then yeah, I prefer to use the one with a common momentum. So then, well, let's remember what we had. I'll write it here just as a reminder. We have phi as integral of IPX, then A of PT plus A dagger minus PT, and pi is integral equal IPX, but then APT minus A dagger minus PT. Okay. All right, so from pi squared I get A of PT minus A dagger minus PT times A of P prime T minus A dagger minus P prime T. Then I get this term. So phi itself comes with 1 over square root 2 omega. The 1 over square root 2 squared with a 1/2 gives the same 1/4. But then I have omega p prime in the denominator now. And the gradient, so here I have a gradient, that's dx, right? Dx will act on e to the ipx and will give an ip. But this is squared, so it's ip squared, that is minus p squared. But one acts on p and one on p prime, so minus p prime. And then this term is also acting on phi squared, so I can put it here as well. And finally, the oscillators of phi are these guys. So A of P plus A dagger minus PT. And the same thing with P prime. All right. Okay. Now let's calculate this further. All right. So the Hamiltonian is equal to so let's do the integral over x first. So I do the integral over x. I get delta 3 p plus p prime. Right? So p prime is equal to minus p. In here it doesn't make any difference. In here it does, so this is now minus p, and this is now p. And here I get plus p squared. And here I get minus p. Here I get plus p. Okay. All right. Yeah, and I got to say then I cancel this with this. Okay. So now h remains just one integral over p. And what is here? Well, minus omega p over 4. And here, here we'll get a did I do this right? I think I did this right. So yeah. So first of all, let me calculate this. So this here is, I remember that this p squared plus n squared is omega p squared. And in the denominator here I get also omega p. So I will cancel one of these with one of these, which allow me to give a common factor. So omega p over 4 is finally a common factor, right, to all the terms. Now let me write here minus a of pt, a of minus pt. Let me write first the terms that should cancel. So plus minus a dagger of pt, a dagger of minus pt. Then the terms that shouldn't cancel, so plus a dagger minus pt, a of minus pt. Plus a of pt, a dagger of pt. So now I've written this guy. Now the second line I will write in a similar way. So this has the overall sign plus. So plus a of pt with a of minus pt. And then plus a dagger of minus pt, a dagger of pt. And then the terms that shouldn't cancel, A of pt plus A of pt, A dagger of pt plus A dagger of minus pt, A of minus pt. All right, now let's try to cancel these terms. So this with this are manifestly the same. So this I can cancel. This with this I can cancel either changing p to minus p, right? Or just commuting A dagger with A dagger since they commute. So this also cancel, right? And this with this, I change p to minus p to show that they're the same. And then this with this, the same thing. Change p to minus p to show that they're the same. So both get a factor of 2. Factor of a quarter gives 1/2. Excuse me. So then I get integral d3p over 2 pi cubed omega p over 2. A of pt, A dagger of pt, plus A dagger of pt. Oh, sorry. No, wait. No, sorry. I did this wrongly, right? Whatever. This was the same as this, and then this gave this. A dagger of pt, A of pt. Okay. So indeed the Hamiltonian itself is also a sum over the Hamiltonians of harmonic oscillators. Remember the Hamiltonian of harmonic oscillator was also omega A dagger plus A dagger A over 2. Okay? So we got the correct result. All right. So we've defined the dynamics in terms of writing what omega was, but we haven't yet explicitly written the time dependence in here. But then in order to do this, remember that if this is quantization, so we're talking about operators, the operators that have explicit time dependence are Heisenberg operators. So we know how to deal with those. So we write that the time dependence is given by the commutator with the Hamiltonian. Right? That's what we wrote. The time dependence of Heisenberg operator is given by the commutator with the Hamiltonian. But now it remains to calculate this explicitly. H is this form. So I just substitute in here. Integral A dagger plus A dagger A over 2. Right? With omega. And here, so I have commutator of terms like A dagger and A dagger A. Right? But this is what? This is just A, right? So that means in here, I will get just A of P and T, but I also had a factor of omega P. Okay? So how do I write this? Well, first of all, remember what this means. So, in general, this thing exponentiates to, so an operator, any operator in the Heisenberg picture, we said minus IHT, right? The reason for that is if I have something like this, time derivative just, well, removes the t, means this is infinitesimal and removes the t, and otherwise this is infinitesimal, the result here is just the commutator, right? So in our case, this is anyway easier. So I could have gotten via this relation, but this form is already exponential. So I can already say that the result is A of P, e to the minus IPT, right? Because I can put this minus I in here, right? So I get this, and then a dagger of P e to the I omega pt. Okay? Good. So we've defined also the time dependence of operators. Well, we've defined for this, and then we can substitute into the formula, well, into these formulas that I kind of sketched in here, that I've written before. And as I noted, the point about so I could write this into forms, one with e to the IPX and in the first term and e to minus IPX in the second, or in this form. This form was easier in order to calculate, but now I'm more interested in the first form because substituting these time dependence, I get that phi of x and t integral dp 2 pi cubed square root 2 omega, but omega p, we found that this is nothing but the relativistic energy of a particle, right? So I'll write this already as 2EP. And then here I get A of P and T times e to the IPX. But A of P and T, as we saw, is A of P times e to the minus I omega t. But minus I omega t plus I dx is the relativistic e to the IPX. So this is written as AT. I can put this as an index. Now e to the I px, where px is just minus et plus px, right? And then the second term had e to the minus IPX, a dagger, but a dagger comes with e to the plus IPT. So this is a dagger p e to the minus I dx, right? And pi of x and t can be obtained, remember, we've seen that explicitly, pi is phi dot, so this is just d dt, pi of x and t. All right? Good. So we have arrived for the free scalar field and a formula that looks more relativistic now. We have these two terms. So now let me consider a discretization, a more precise discretization of the field in order to consider the equivalent of the Fock space for harmonic oscillators. Remember that harmonic oscillators have a Fock space, an occupation number space, and correspondingly the free scalar field, which is just a collection of harmonic oscillators, will have also a Fock space. But to do that more rigorously, we need to discretize the field in order to have a well-defined number of states. Now, the discretization that I did before was a little bit hand-wavy, and it served only the purpose to define correctly the canonical quantization relations and the Poisson brackets and all that. But now I'll do a more rigorous one. Considering that we are in a finite volume or box of size V. If I do that, so that's certainly a physical condition. Most systems that you can think of can be thought of as having a finite size. I mean, if nothing, just because of simplicity. After a while, it doesn't matter if there's more outside. So when I do this, I'll of course not discretize space by doing that, but I'll discretize momenta, which is good enough because, as we saw, the fields themselves were just sum of a momenta. Integrals are now become sums of a momenta of harmonic oscillators. That's all I need. Okay? So let's say that in a direction z, I'll have a length Lz. That means that now momenta are quantized to be 2 pi n over Lz, right? This is discretization. So this is now a correct discretization. It's a physical one. And then integral d3k becomes 1 over v sum over k. Right? This is basically taking products of these things. Right? You will see k is 1 over L times m. So that means integral d3k is product of 1 over L, 1 over v times sum over k. And then d3k minus k prime becomes v delta k minus k prime, right? Because this is integrated over k to b1. So I take the product of these two things, I need to get 1, right? However, we still need to do a redefinition in order to avoid some annoying factors, I'll redefine my my oscillators A and A dagger with respect to the volume and some 2 pi's. So I'll write this as square root V times 2 pi cubed times an alpha. And then we have the Hamiltonian as integral d3 p omega p over 2 a dagger plus a dagger a, right? And now I can write this in a discrete way. The integral is 1 over e times sum, but then a dagger comes with this factor. Oh, sorry, here I actually also have 2 pi cubed, right? So now we see the point of this factor, because now it cancels this factor, so the integral became 1 over v sum, and then v 2 pi cubed will get cancelled by the square root of this factor, and we'll just get sum over k, omega k over 2. If you want, you can remember there's an h bar. And then alpha k, alpha dagger k, alpha dagger k, alpha k. Okay, so now this is truly the sum over Hamiltonians of independent harmonic oscillators. And I remember then that I can put this into the form nk plus a half. So this is a dagger, sorry, alpha dagger k, alpha k. But if I do this, moreover, now nk has the interpretation of an occupation number, right? Then nk is occupation number. So one defines a Fock space of states defined by occupation number little n, which is the eigenvalue of capital N, right? And moreover, we know how to define this from quantum mechanics, as means that we need to act, in order to obtain this state, we need to act n times with the creation operator a dagger, in this case alpha dagger. So n is, well, there's some normalization, and then alpha dagger to the n acting on the vacuum, right? So the normalization is such that these states are orthonormal. Right? And so alpha dagger is creation or raising operator, and alpha k is annihilation or lowering operator. And the nomenclature comes from the fact that when acting with alpha and alpha dagger on such a state n, you get a state with n minus 1 or n plus 1. That is to say, alpha k acting on n gives square root nk, nk minus 1, right? Whereas alpha dagger on nk. Here's current nk plus 1, nk plus 1. Right? And then the Hamiltonian on the state nk is omega k, nk plus a half, k. All right. So from this we see that nk is a natural number. It's the occupation number of the state. Okay. So these are all things that were clear from quantum mechanics, the harmonic oscillator. But by discretizing momenta, by putting the system in a box, we have obtained that the free scalar field is nothing but a sum, well, a countable sum. It's still infinite, but it's countable. Remember that n in here is still, well, z in this case, it's an integer, right? So it's an infinite but countable number of the system of harmonic oscillators. And since each of these harmonic oscillators corresponding to a frequency has this Fock space or occupation number space, we can also write down a Fock space or occupation number space for the whole scalar field. Fock space representation sometimes called, but and so the point is, since the Hamiltonian itself can be thought of, the Hamiltonian itself can be described as the sum of, let's say, the sum of harmonic oscillators. That means that the corresponding Hilbert space will be just a direct product of, how should we call them? Yeah, HK, the Hilbert space of the harmonic oscillator. Okay?
So this new Hilbert space is what we call Fock space now?
Yeah. So this is then characterized by a series of numbers nk, each occupation number nk for each, one occupation number nk for each momentum k. But this is just a product space, a tensor product space, therefore the state itself can be thought of as product of a k, or maybe product or tensor product if you want, of these nks. So let's say nk1 times nk2 times dot dot, right? However, each of these states is thought of as the action of a creation operator of the corresponding k to the power n acting on some vacuum for this harmonic oscillator. But we can define the total vacuum as the tensor product of the vacua for each k, right? The obvious notation. Vacuum is when all the harmonic oscillators are in vacuum. And then just write this product as just a product of operators acting on a single vacuum. Okay. So in other words, we define this by saying that alpha k 0 is 0 for all k, right? All right. Well, now I want to make the same observation that I already made before, but there was a kind of a preview. So I want to define the so-called normal ordering. And we saw that the Hamiltonian of a single oscillator had this 0-point energy, the energy of the vacuum for the harmonic oscillator. And well, this is extremely small. Perhaps you don't care that you shouldn't be able to see this, it's the vacuum. So for one harmonic oscillator, you might say, well, who cares? But now we see that we care. So now we have the 0-point energy, or vacuum energy, is 0. Now is sum over k of this h bar k omega over 2, right? Sum over all the k's. But remember that the k's are countable. There's an infinite number of them. So this, first of all, diverges. Right? Well, then you might say, if I put a system in a box, you know, this will give some energy density. Moreover, the sum over k has to be cut off somewhere at Planck scale or something. So yeah, it's not infinite, it's just very large. So there's a very large energy density. By dimensional reasons, you can figure out that the dimension, that this has to be proportional. The energy density has dimensions 4 because it's energy over distance cubed, but the units of energy are the same as the units of 1 over L. So this is the same as energy to the 4th. So by dimensional arguments, you can figure out that this has to be of the order of the cutoff to the 4th. Right? So you get the energy density of the order of the cutoff to the 4th. The cutoff is what? N Planck. So N Planck to the 4th. And N Planck is 10 to the 19 GeV to the 4th. You see, this is an absurd number. So if you would observe this, this would be an incredible amount of energy. It's about 120 orders of magnitude higher than what we actually observe. So this is this is an actual problem, a very important problem, what many, including myself, believe to be the most important problem of theoretical physics, called the cosmological constant problem. The fact, just a moment, the fact that the energy density and corresponding energy would need to gravitate, would need to cause the universe to collapse, therefore be observable, and such an absurdly high amount of energy would lead to the universe never appearing at all. And that means that there is something that we're still missing in the very, very basic, the most basic of models about quantum field theory, a free scalar field. And there is no good solution to this yet. Yes?
Why would the Scalar be close to the Planck's mass?
Well, because we don't know of any other natural, you know, the Planck mass is also the simplest things we can think of, the most natural things we can think of, give quantum gravity at the Planck mass, because the Planck mass, or energy, is obtained by taking the three constants that we know of, Newton constant for gravity, C for relativity, and H bar for quantum mechanics. And out of this you can find a unique combination that gives EP, that gives an energy. You can see this in the system where I put H bar equal to 1 and C equal to 1. EP is of the order of 1 over square root Gn. Gn has dimension 2. And so that tells us that all things being equal, we expect quantum gravity at this scale. And now you take all the other scales that you can make from physics, and you see they're all much smaller than that. So the highest scale that you can make from non-physics is this one. And that's why you believe that, you know, this is a relevant scale and the highest that you can think of. That's the only reason why I put the cutoff there, but perhaps things are not equal, and there are more ways to consider fundamental scale lower and even higher if you want. So that's not the full proof argument, sure, but it's an argument that, I mean, simplicity, or naturalness, is a concept that seemed to have worked until now, so people believe it's worth something. So, of course, you could just be agnostic and say, well, energy density is what it is, I don't care. But, yeah, that's not a very good answer. All right? Good. So, the other point is, so you can't observe this, but it's important to realize that you can observe something. If you will see this at towards the end of the class, of the course, we'll see that there's something called the Casimir Effect. So this energy density is energy divided by L cubed. So it depends on L, on the size of the box. And now if I can somehow vary the size of the box, then I can certainly observe those variations in energy. And that is the so-called Casimir effect that's been measured. So you can measure the force, that's gradient of some energy. And that energy is this zero-point energy. So we implicitly know that at least its variations, which are finite, are valid. So it's not like this thing is complete, dragon or something that you don't care. You cannot know whether it exists or not, right? The point is that you can actually measure its variations, so it's kind of natural to assume they can actually measure the whole thing. That's the problem. All right, but if we ignore this nevertheless, So the statement is, we just drop this constant from our calculations. And as I said, that is what we call normal ordering. We just define that the normal or natural ordering is such that I always put a dagger to the left of A, even if initially in my formulas they are in the opposite order. So then I define the normal order Hamiltonian, right? The normal order Hamiltonian. And then this is just the Hamiltonian minus this troublesome constant, right? Which is just this this thing that depends on occupation numbers, on things being outside the vacuum. So that's semi-finite. Okay? And the point about this normal ordering is we assume that all observables are normal ordered. So we assume that when we take some vacuum expectation value, of some operator, that it should always be normal ordered so that we get a finite result. One more observation that I want to make is that we've seen that we obtained in phi, we obtained these combinations. We obtain AP e to the IPX plus A dagger P e to the minus IPX. And then P0 here was this EP, the energy, the relativistic energy of a particle. But that means that this thing has E minus I EPT. This has E to the plus I EPT. Right? So that means that we create positive energy, but we annihilate negative energy. So we have only positive excitations. However, all that I've said today was for a real scalar field. Okay, with the scalar field I've considered today was a real function. I never wrote a phi complex conjugate anywhere. Everything I described was in terms of a single real function. But next time we will consider complex fields, which can be thought of as two real fields together. But more importantly, if you take complex fields, we will see that we will obtain all the possibilities. We will create and destroy both E positive and E negative, and that will come with the concept of antiparticles. So the negative energy states in some sense are related to the existence of antiparticles. It's a kind of hand-wavy relation, but it's a useful one to make. So what we can say here, if one wants, is that the real scalar field is its own antiparticle. It doesn't have a separate antiparticle. But the complex scalar field will have antiparticles. All right, so just in case you're wondering about that, you've heard somewhere. And finally, the last thing I want to say today is about Bose-Einstein statistics. So, as I said before, there is the so-called spin statistics theorem that says that fields of integer spin, in particular the scalar field, which has spin 0, are related with Bose-Einstein statistics, whereas fields of half-integer spin are related with Fermi-Dirac statistics. So we have to see that this scalar field is related to Bose-Einstein statistics. But, of course, one of the things that we used was that the creation operators A dagger commute among themselves, right? So what does that mean now for some physical state? So I've shown to you the Fock space representation, which is a basis of states, right? But the general state is some combination of all of these states with some complex coefficients in general. So a general state would be such combination where the coefficients are called the wave function, right? So let's imagine that I have a state with two particles, a general state with two particles. Then this would be a sum of a K1, K2, then alpha K1 dagger, alpha K2 dagger, acting on 0. So that's my Fock's the basis state of the Fock representation of two particles, two creations operators acting on a vacuum. But then with a wave function psi of K1, K2, in other words, a coefficient for each of these states, right? But if this is true, and well, then also the alphas, then I can commute these two and then rename K1 as K2 and K2 as K1. And so rewrite this as sum of K1, K2, psi of K2, K1, alpha K1, dagger, alpha K2, dagger, acting on the vacuum, right? From these two, I deduce that I must have that the wave function must be symmetric in the exchange of K2 and K1. In other words, Bose-Einstein statistics. Right? Well, we'll not do this here, but we should note that what happens for a fermionic case. I can consider a fermionic oscillator, and we'll do that in more detail later, but roughly speaking, we'll get that a Hamiltonian instead of A dagger plus A dagger B, sorry, yeah, B dagger B minus B dagger. And so it's, in this case, one really has to define that the anticommutator of B with B dagger is 1, such that this becomes, as before, proportional to BB dagger, just that then the constant is minus 1/2. Okay? And then this will lead to Fermi-Dirac statistics. All right. So, okay, so here you could see a way to get rid of the cosmological constant problem. Well, it seems. Since the energy of the fermion is with minus 1/2, if I have equal number of states for each energy, I have equal number of bosons and fermions, then this constant cancels, right? That is called supersymmetry, by the way. So n ak is equal to n bk, let's say. So that seems to solve it. So anybody can tell me why this is not a solution? Do you see supersymmetry? No. So it's not a it's not a solution. I mean, even if the world is supersymmetric at some high scale, still the low energy world is not. So the cutoff is just perhaps lower than the Planck scale, but not too low. Right? Because we don't see supersymmetry at whatever energy we can probe, we don't see supersymmetry. So we just put the cutoff, you know, at least to the maximum energy we can see. So let's say 10 TeV we can see today. All right. All right, so this is what I wanted to tell you today. Do you have questions? All right, everything is clear? Good. So then please give me exercises. I haven't corrected them yet today because some people had to give in late. Yeah. All right. Pode sim.